My great pleasure to introduce Daniel. He was a student from the first edition, I guess, right? 2007? No? 2009? Well, at some point you were here before, right? But so he did his studies with Marcelo Terra, master as well. And after he moved to a PhD in ICFO with Tony Assim, then a postdoc in Singapore. And since then, he's a researcher in ICFO, in Barcelona, has written many important papers, has a lot of important grants, and has written, well, the famous Bell non-locality review. So we really have the great expert here with us. So let's please thank Daniel and start learning from him.
No. Yes, so I need help from Barbara, yes. So thanks a lot, Planet, for the introduction, and thank you all the organizers for inviting me. It's really an honor to be here. I came, I think, every edition of Paraty, never as a student, but yes. The part of many grants is wrong, so don't take him seriously, and the famous paper is also wrong. Okay. So I will go straight to the point because I have many things to say. So let me count the time here. So okay, so when they invited me to give you this course, I was thinking, so what to teach, and so I think, so you here probably work on different things. So most probably in something in quantum information, but this can be totally different things. And I don't know if in the future you'll be working on quantum information, or maybe you will switch to another field. So I thought I could teach you something that could be useful for you for whatever you do. Okay, so this is why I decided to give this introduction on semidefinite programming. So semidefinite programming is a type of optimization problems that appear in many problems in not only in physics but in engineering and many other fields. But in particular in quantum mechanics it appears many times. Okay? And it happens because this expression semidefinite there comes from matrices which are positive semidefinite. Okay? And as you probably know, quantum states are described by operators which are positive semidefinite. Okay? And measurements also are given by operators which are positive semidefinite. So if you are optimizing, so if you have in many instances you have a problem that you are trying to optimize some function with respect to quantum states or with respect to quantum measurements. So this fits perfectly in the framework of semidefinite programming. But then I didn't want to simply teach some tool, numerical and mathematical tool, but I wanted to give you to teach this with some motivation. Okay? So I think we always learn better if we apply this technique to a given interesting problem, and this is why I decided to apply semidefinite programming to the problem of quantum correlation. Okay? So this is the idea of the course. Okay? So let me give you some references, okay, before we start. Okay, so I promise you that by the end of this event, I'm gonna provide some lecture notes. Okay, so I will ask the organizers, I don't know, to share with you, send by email or put in the web page. So everything that I'm going to write here will be available in a PDF by the end of maybe this week or next week. Okay? But anyway, so let me give you some references and just comment to you a little bit about them. So let's say the Bible of actually convex optimization. So semidefinite programming is a type of optimization problem which fits in this more general type of optimization problems, which are called convex optimization. Okay? So, and this is a book by Boyd and Van. This is kind of the Bible of convex optimization, and it's free. Okay? So if you Google their name, you find this book. It's for free. It's very nice. It's a bit technical, but it's a very good reference. And then something that is more related to quantum information is the lecture notes by John Watrous. So it's actually lecture notes on quantum information, but if you go to chapters 7 and 8, it's about semi-definite programming, and it's more focused on quantum information. Okay, and then for the part of quantum correlations, so you may know the review by the Autodesk family. I forgot to put the name there. So you have this review on reviews of modern physics that's called Quantum Entanglement. It's a bit dense as well, but it's a good reference. And then, so during the course I will try to talk about 3 types of quantum correlations: entanglement, steering, and non-locality. So for quantum steering, so together with Paul Skripczyk, we have a review which is quantum steering from the point of view of semi-definite programming. So I think it's so nice reference for this purpose, because again, so it's like applying semi-definite programming to a concrete problem. And actually in this review, so we provide all the codes, okay, all the SDP codes that we use in this review. It's there, it's available. Then there is a more conceptual review for steering. So it's quite new by the group of Ziegen. And then for Bell non-locality, there is the famous review, these reviews of modern physics. And so there is a very recent book by Valerio Scarani that's also called Bell non-locality that I really recommend. Okay, that's very, so he introduced the subject in a very smooth way. I think it's very nice. Okay, so my idea for this course is the following. Okay, so I'm going to start today with the introduction to SDPs, semi-definite programming. And then after that, I'm going to, jump like topic by topic to this type of correlations. Okay, so quantum correlations. I will talk about entanglement, steering, non-locality. Okay, so the way I organize the course is the following. So today I'm going to talk about this, okay, only SDPs. And don't be shy, interrupt me, make questions at any time. So if we discuss SDPs for the whole course, I'm already very happy, okay, so we can stay here. And then, so in the next lectures, I will probably talk about entanglement and perhaps steering. And for the last one, I will talk about non-locality. And this thing here, I don't know. It will depend on how it goes, okay? One thing that I would really like to do, perhaps in the last 30 minutes of the lectures, is to really show you, so it's these implementations, really show you how it works in practice, okay? So I'm going to show you the codes, okay? And how you write the codes and so on, okay? But so I could talk about other problems, and then, so how many experimentalists are here? Okay, we have quite a few, right? Okay, so I don't know, perhaps we can discuss. So instead of talking about different problems, I can try to talk about experimental issues, okay? How to deal with experimental errors or finite statistics in the framework of semi-definite programming, okay? All right, let's start. Okay, so I will start. So I apologize for the written thing here. So it's the first time I give a lecture using this technology. So I will start. So my prayer. Okay. So I'm going to start with actually something that is a subclass of semi-definite programming, which is linear programming. Okay? So, and I'm going to do this because this is linear programming, okay? So it's called LP, okay? So you are probably more familiar with linear programming. So I will recall linear programming for you, or sometimes called linear optimization. And then, so you see that the generalization to SDPs is quite smooth, okay? So the idea of linear programming is the following. Okay, so you have a bunch of variables, okay, xi, so I can be from 1 to m, okay? So I have m variables, and then what I want to do is to maximize, a linear function of these variables. So I'm going to write like this. Okay, where these AIs are coefficients. Okay, so subject to some constraints. Okay, and the constraints are also linear constraints. Okay, so I don't know what's going on. I have some linear constraints here, okay? So I have xi is equal to b1, okay? b2. Okay, so what do we have here? So what we are doing is we are maximizing a linear function of the variables, given that there are some constraints, okay? So there are some other linear constraints here, okay? So those are coefficients and those are my variables. So we have some inequality constraints, okay? Also linear, and we have that all the variables are positive, okay? So just to set the notation here, okay? So again, so those, the xi are variables, okay? Okay, so this thing here is called the objective function, okay? Okay, so this is the linear function that we want to optimize, that we want to maximize. It's called the objective function. So we have equality constraints. Okay? So we have a bunch of inequality constraints. And we have positivity constraints. So, is it clear? Okay. Right. So, and then, of course, okay, one thing that I should say is that, so here I just wrote one equality constraint and one inequality constraint, but I could have many. Okay? I could have several constraints like this, several constraints like that. Okay? So, okay, the second thing I would like to say, this is just to give you some nomenclature. So the set of vectors that satisfy all the constraints are called feasible points. Okay? So if so what's the point here? So there exists values for these variables xi which satisfies the constraint. Okay? Those are the feasible points. So for the code, what I'm trying to find is what's the maximum of this linear function, the objective function, among all possible feasible points, okay? All the points that satisfy the constraints. And the solution, okay, it's called the optimal value of the SDP, okay? The maximum. So other things that I have to say is that, okay, here I wrote maximize, the linear function, but I could also have minimize, okay? So actually, the maximum of a function is equal to the minus the minimum of minus the function. Okay, so I can do both maximizations and minimizations. And also here in this inequality constraint, I put this symbol of less or equal than B2, but it could be greater or equal to. Okay? This is completely general. Okay? And here, so of course I can also write this in a more compact form that I'm going to put here, because when I write the SDP, you see that it's very similar. Okay? So you see that I'm maximizing this linear function. So I can write this as the maximum of a vector A, which is the vector of coefficients, and X, okay? Which is a vector containing all the constraints. Can you read? Can everyone read this? Yeah. Okay. And then I have subject to, so the first constraint I can also write as an inner product, okay, which is equal to B1. So it's beta times x vector, beta times vector x equal to B1. And then I have vector gamma times vector x smaller or equal than B2. Okay, and I have this vector x is positive, okay, where this positive greater or equal to is to be understood as element-wise. Okay? So what I'm just doing here is, so I put all these coefficients ai into a vector, all the variables into a vector, and then this linear function here is simply the product between these two vectors. And the same thing for the linear constraint and the inequality constraint. And then I have that for the positivity constraint, that this vector x is positive, where this symbol here is to be understood that every element of this vector is positive. Okay? All right. Okay, so if you got this, then it will be very easy to go to semi-definite programming. Why? Because now in semi-definite programming is a very natural generalization, which is given by the following. Okay, so again, I have a, now I have, okay, so now I have maximization, okay, maximize, so the trace of A times X, where now A and X are matrices, okay? So, and you see that, so this is the kind of the inner product between these two matrices, which is kind of similar to here, okay? So here we have two matrices, and we are maximizing the inner product between these two matrices. This matrix A is a matrix of coefficients, so those are non-numbers, and this matrix X is the variable, okay? Now we have this variable, and, okay, so such that, so now we have again, a linear, so we have a linear constraint, okay, that I'm going to explain you in a second. I have, again, a inequality constraint, okay, and I have a positivity constraint. Okay? So you see that the structure is the same, okay? So I'm maximizing a linear function of x. Actually, if you open this trace here, you see that this is simply a linear function of the elements of x. It's exactly like that one. Okay? So here I have a linear function of the elements of x. So here I have a linear constraint, and this linear constraint I wrote like this map on x is equal to this other matrix. So this thing here, so this phi 1, let me write here. So phi 1 and phi 2, okay, are linear maps that respect hermicity. Okay, so this is a map that applied to x. X is an Hermitian operator, okay? So gives another Hermitian operator, and it's a linear map. This means that this is a matrix for which every element is a linear combination of the elements of x, okay? And this is equal to B1. Okay? So again, so if you see you can see this as exactly this type of constraint, okay? Why? Because so every element of this matrix is a linear function of the elements of this matrix. Okay? And then I have that each element is equal to one element of B1. So I have several linear constraints, okay, on the elements of X. So here is similar. I miss a 2 here. So, okay, again, so here I have phi 2, okay, so this map applied to X, this again is a matrix, which is a linear, so this is a linear map on X, so it's smaller or equal this matrix, okay? So, and here, these two things here, and this is very important, this is a matrix inequality. Okay? So this means that, okay, when I put smaller or equal or bigger than equal here, so this means that all the eigenvalues of this matrix are smaller than the eigenvalues of this matrix. Okay? Yes, okay, and then, so here I have that all the eigenvalues of this matrix here are positive or equal to 0. The difference between these two is positive, yes. Mm-hmm. The difference is positive, yeah, so this matrix minus this matrix, or this matrix minus this one, okay, have all the eigenvalues positive. Is it clear now? Right. Yes, yes, okay, so yes. Mm-hmm. Yes, B2 minus phi 2 of X is positive, which means that B2, this matrix, that is B2 minus phi 2, has all the eigenvalues positive. You got the point, no? Right. Okay, so one thing that... I have
another question.
Sure.
Sorry, the microphone. I was the first one to forget it. It's a bit technical. When you diagonalize phi 2 of X and B2, it's not necessarily in the same basis.
No, yes.
So you could reorder the eigenvalues. So it suffices to say that you just find a bunch of eigenvalues so that the B2 ones are always bigger than one of, if you find a set of, an ordering of B2 eigenvalues that's bigger than an ordering of the phi 2?
Actually, what you have to do is exactly to take B2 minus phi 2, diagonalize.
Okay, yeah.
And then you need all the...
So they diagonalize in the same basis, okay,
yes,
in a sense.
you
Yeah.
diagonalize the difference between the two.
Okay, thanks.
And then, so, and now here you, the difference between the two, okay? Because when you make this diagonalization, what you have are like a non-linear functions of the entries of X. Okay? And this is why this is a generalization of this. Here I only have linear functions of these variables xi. Okay? And here I have non-linear functions of the variables x, which are the elements of this matrix X, because of you have to diagonalize the matrix. Okay? So, and another thing that you can see, so you can also see this difference exactly in the type of inequality. So if I actually take these to be element-wise inequalities, I would recover exactly this. Okay? Right? Which means if these matrices are actually diagonal in the same base, okay, I would have, if I only use diagonal matrices here, I would recover a linear program. All right. So, okay, so this is the definition of a linear programming and SDPs. So let me give you an example, okay? So which will make it easier to understand. Okay, so let me already give you an example on the context of quantum information, and the example will be the following. Find the maximum, or it could be the minimum as well, eigenvalue of H. Yeah. Yes. Oh no, you cannot make question. You are an expert on this thing. Yeah, you.
So do you have to learn something about Okay. So do you have to demand something about A? It should be Hermitian or something like that, like for the trace of AX. Could you put there any matrix I don't think so. I don't remember.
It should be real, I guess. So I think it should only be real, no?
Yeah, that's a...
Okay, so actually the trace of AX here, so the trace of AX is actually a linear function of the entries of X. A real function. Okay. So it's exactly like this. So, okay.
Okay.
So I could have written exactly the same linear function here.
Okay.
I only did like this to write X as the variable of the XDP. But this should be a linear function, a real linear function of the elements of
okay, thank
X.
you.
Yeah.
Hello, I didn't understand why you said that it's a generalization because phi2 of x won't be necessarily linear in function of x as the element of x, because for me if it's a linear map that I have a combination of x as input, doesn't mean it mean also that it's a linear, I mean the condition will be a linear expression of the coefficient of the matrix x in the end? You said something like this, I think. I'm not sure.
Okay, so you can see, so Y and SDP is a generalization of a linear programming, so I cannot see with this light. So this is the question, your question is?
Yeah, you said it's not necessarily linear in the term of the matrix X.
Yes.
And I don't see, for me it should, but I don't understand that.
No, for example, take a, let's say, take a 2 by 2 matrix, okay? And then, so let's find the eigenvalues of this matrix. So if you do the calculation, you find that you have to solve a quadratic function of the elements of the matrix, right? So you see that because, so this imposes that the eigenvalues of this matrix are positive. So actually, if these will give me a set of equations which are not linear on the elements of X.
Okay. Okay.
Okay? So
because we look at eigenvalues.
Yeah, so that's the point. So it's linear on the matrix, right? So on the matrix X. But it's not linear. So this equation, so this is actually a set of equations which is not linear on the elements of X.
Okay. Okay.
Right.
I just want a quick, stupid question for clarification. When you have matrix A and X, you're generalizing, right? Because it's not, the trace of AX is not the scalar product that you wrote unless they're diagonal. Right? Like A1, X1 plus A2, X2 plus A3, A3. If I take A times X, right? So I just want to know exactly if A and X have to be diagonal or not.
No, they don't have to be diagonal.
So it's more general.
So if you take any matrix A and X, so this expression, the inner product, so this will be a linear function of the elements of X.
Yeah.
So and this I can write any linear function in this way. Okay. Like I can write in this way or can I write in that way.